YouTube stream before I forget. Start the music before I forget. Music, I think that'll be at a good level. Okay, so Minesweeper, no guessing mode. Also, hi Thunder, congrats on the first. Oh yeah, like Minesweeper is a stupid enough game without the guessing. With guessing, it's hardly even a game. I play way too much Minesweeper. All right, wait. For first, let's like stretch out. Get ready. This is a very physical activity that we're about to do. Shit. No guessing my ass. This isn't guessing. Near me. Hey Parth. We doing well. Bam. 48 seconds, not bad. Yeah, that I just got like mentally stuck for a second because I thought I couldn't progress, but I actually could. What is evil mode? Let's see. Oh, it's just a massive one. Meh. Yeah, Parth. I was just warming up with a Minesweeper, I guess. Thanks for redeeming that Thunder. I'm gonna turn these down just a teensy bit. Okay. So we have options for what to do. I don't know what I want to do. Do I play chess? A little bit. Like maybe 1150 on chess.com. That secret you've been guarding isn't. I guess your secret is out, Thunder. Whatever secret you were keeping, people know. Movie rating inflation is real. Thank you so much for the raid, Zach. Movie rating inflation is indeed real. Hope your stream was good. I guess I was watching it, so I know. If you want to play like a quick game of chess, we can do that. Maybe like a 3-minute game. Do you prefer chess.com or Lee Chess? I can do either. Welcome in, people. That E&M thing that you're gonna do is really exciting, Zach. Lee Chess? Okay. See if I can remember how to make games. Challenge a friend, probably? I mean, if you knew what you were doing, it wouldn't be worth doing. Maybe 3 + 2, if that's okay, Parth. Casual. And then hopefully... Okay. So Parth, I'm just gonna hope that you're the first person to click on this. It would be cooler to me if you did the whole like special relativity thing and magnetism, but you'll still learn some cool stuff even without that. And so I promise we will be doing some math today. I've got both mathematical oncology homework queued up and PDEs homework queued up, but the stream only just started, so I'm kind of messing around. And to be honest, this is nice because I'm not sure what I want to work on right now. So this is letting me procrastinate on deciding what to do. This is an interesting opening choice. Do I mind that? Actually, you know what? I think I should take. With the pawn? That's a choice. Hmm. We have choices here. I think I like doing this. Oh, you pre-moved that. You read me like a book. Um Ooh. What do we do here? I don't know. I should stop using so much of my time though. That's for sure. Why did I do that? I don't think that was a good move. Because of that. That's why it was a bad move. Um. Well, shit. Okay, but this is not the end of the world. So I can play this. I think we're hanging on here. What are you doing with that queen? Rip a pawn now. Hmm. Shoot, I need to stop using up all my time. I need to move faster. Um. uh. I know. I saw it right after I moved, and I didn't want to say anything because I assumed Barth was listening. Uh, I just threw. I just threw. Uh, aha! I got a pawn back. This is all going according to plan. I can't even talk. Wait, did I blunder mate also or something? Was there worse? I blundered my queen? Oh, I didn't even see that. I guess neither of us saw it though. I'm about to lose on time anyway, even if I didn't blunder. I'm suddenly back in the game now. We have to play fast. Fast and furious. Actually, family. Okay, just as long as I don't mess this up. Which is a big if. Hey, Suckno. This is an insane plot twist, Raven. Absolutely. What you gonna do, Parth? Winter is coming. My pawns are coming. Because we're both pretty low rated. Games are never over until they're over. Your efforts will be rewarded. Be patient. Ooh, that's a good fortune. Hey, Rex. Von Neumann? Wait. Oh, okay. I thought I ran out of time for a second. All right. GG, Parth. Thanks for the game. Hey, Aditya. We will get to math now. Oh, yeah. Okay, never mind. We won't get to math. Let's check the move where I apparently blundered my queen. Wait. Wait, I should have just taken the queen? Why is this good? Am I up material here or something? I don't think I am. I'm up one pawn here, but why is this better? So wait, okay, so I straight up blundered my queen. I don't know how I only saw the bishop blunder. Oh my god. Yeah. GG, Parth. Alright, well, that's why I barely play chess, because I do stuff like that. Let's see what this theorem is that Socknow was talking about. Rational choice under uncertainty involves making decisions that take the form of maximizing expected value of the cardinal utility function. Ooh. We both did, Parth? Only Thunder saw it, apparently. This only Thunder said something. This feels like, this is kind of cool. I didn't know that von Neumann said stuff like this. This feels kind of like a calculus of variations thing. That might just because I'm taking a calculus of variations class right now. Like, mix in with probability. Yeah, it was a good game, Parth. you have diminishing returns, you always have a convex optimization problem, so there's always an optimum. Hmm. I don't know where diminishing returns is coming in here. This is pretty cool though, so far, Sock now. Yeah, let's see the axioms. Completeness. What the hell is this symbol? Is that is that greater than or equal to? I don't know. I think it's greater than or equal to. Why does it look so weird though? Connection with Arrow's theorem. Okay. Lip kiss? Chill crunch? Oh, what, like, that's what the symbol looks like? Oh my, it does look like kissing lips. I didn't even, I had to look at it for a second. PhD also sees it as a kiss symbol. Okay. The first story that we have a total pre-order. Oh, is this not quite greater than or less than? It's maybe something similar, but not exactly. Symbol for preference? Okay. Two things with equal value is the thing, but they're different things. Oh god, Parth, I've tried JE advanced questions before and I just can't really do them. I'm sorry. The best I could do is Google it, but I think you can Google it too. In the last paragraph of setup. Okay, yeah, fair enough, Max. Oh, okay. If M is either preferred over or viewed with indifference. Okay, okay, okay. So it is like a greater than or less than, but just not. Um. Oh yeah, absolutely. Just not necessarily with numbers, I guess. Continuity. Probability. That one's a little hard to read. But okay. Turn into you can assign real values to all of these things. Probably. Independence. The irrelevant part of the lottery underlined. Hmm. Okay. So what's the actual theorem then? For any Vnm rational agent satisfying these axioms, there exists a function u which assigns each outcome a real number u of a, such that for any two lotteries, L less than M, I'm just going to say less than, if and only if, E of u of L is less than E of u of M. Hey, Skirtle, doo-doo. So this actually does feel like a calculus of variations thing, but maybe like discrete. It's cool. Thanks for sharing it, Sockno. Your mode of life will be changed for the better because of good news soon. Hmm. Yeah, that's kind of weird for it to be nice. Hopefully the good news is us killing that boss in Windrose. Which hopefully I'll have more time to play it over the week. This week has been messed up for me with classes. This is interesting because I can solve a calculus problem with the utility function u. We're going to replace u with f of u, where f is any, let's say, smooth to be nice increasing function. So the problem will be the same. Oh, okay, yeah, fair enough. He is a tank. And I bet it was like probably a lot harder for you with your ping too. Um, utilities like square root xy to make it easier, just say u equals xy. Okay. And that's easier to work with and solve a problem with. Okay, so I'm trying to decide right now between, unless someone wants to ask me a question, between PDEs. This is PDEs and cancer modeling. Or Minesweeper. There we go. Decision made. Skill and gear check boss. Yeah, that's fair. All right, enjoy. I don't even know what barony is, but enjoy it. Paper that has really abused this type of modeling to give a very silly model. Okay. All right, with your guys' help, we can do zero math this stream. Just keep on redeeming Minesweepers, asking to play chess. These are really just excuses for me to like goof off. Um, Bam. 39 seconds. That's 9 seconds better than the one that I did at the start of the stream. Thank you for redeeming that PhD. Slay the Spire 2? No, I've heard of it. I don't know much of anything about it though. Culture and customs of China attract you. It knows you're learning Chinese. Wow, that's really cool, Max. That must be really difficult to learn. You're also going to see if you can see how I can find the ordinal back formation and rated and approval voting, because in von Neumann, he's saying that ordinal systems imply cardinal systems. So you can see in the wiki. So I think I can find a way to debunk these two voting systems. Okay. Interesting, interesting. Hey, Clonk. So-so is good, very excellent good, and yet it is not. It is but so-so? Did William Shakespeare actually say that? Hope you're doing well, Clonk. I have no idea what that means. Linear algebra exam coming up. Ooh. Jordan canonical form of a matrix larger than 2 by 2. Wait, Jordan canonical form? Like, Jordan canonical form. Is that what I'm thinking of? Jordan normal form? Oh, okay. It's this. So can you calculate this for any matrix? Assuming it has all its Or like, I guess you could do it for any matrix. Any square, fair, yeah. Little broing me? Damn it. I'm probably like 10 years older than you, syntax. Why is there a... Oh, I get why. Okay, I was wondering why there's a one here, but not ones up here on this diagonal. But that's because, like, you need at least two repeated eigenvalues to have a one there. Maps from V to V. Okay. You know, I kind of, like... I don't know what it'll be useful for, but I do kind of wonder if someone has done linear algebra with, like, three-dimensional matrices. I don't think that would make much sense. But, like, we only ever do, like, two-dimensional matrices or one-dimensional vectors. I never seen a reason to go to, like, a third. Oh, are those tensors? Maybe I'm wrong. I don't know what a tensor actually is. I just know it's something like a matrix. From tensor rank is very difficult. Okay. Let's just look at a Wikipedia page, I guess. Think of it three tensors a whole field. Okay. Oh, okay, fair enough. I guess these are just tensors, and I just don't know what tensors are. Hey, Anti-King. If you mean in general, I'm a master's student studying applied math. If you mean like right this instant, I was just looking at the Wikipedia page for tensors. Unless someone asks a question, though, I'm gonna either do homework from my cancer modeling class or my PDEs class. I'm not sure yet. Thank God, Leo. I'm gonna need that. I recently learned eigenvalues and vectors. I remember you saying that when I gave you an invariant line question. Oh yeah, I don't remember your invariant line question. Hey, there you go, Leo. There's your chance. So the first thing that you need to do is when you have just like, let's just do a 2x2 matrix for simplicity. I forget what example we were using the other day. Maybe it was 1, 2, 3, 0. I think this turned out to have nice eigenvalues in vectors. But yeah, just like think of any 2x2 matrix as a transformation of your x and y plane. So if this is your x and y plane before being transformed and you have some vector going this like direction, after applying the linear transformation, it's going to be like potentially scaled like bigger or smaller and pointing some other direction. That's kind of like generally what a 2x2 matrix will do when you multiply it by a vector. But it turns out that not necessarily every single matrix, but most matrices have, if we're talking about two by two matrices, there will be two distinct directions where vectors do not change the way they're pointing. They might still scale bigger and smaller, but it will not change direction. And in linear algebra, that's the more important thing. That's the thing that you care about, is direction. So when we're talking about invariant lines, you can think of a vector as basically just a line in the xy plane, and it's what lines do not change slope after you multiply by this matrix. $25. Ben's, thank you for the follow. So yeah, if you want, we can actually go and calculate some things. but if that's what you wanted to hear, I can leave it there. Not wishy-washy aimless vectors. Yeah. When I was sick, I kept blowing my nose so much the skin ripped inside my nose. Oh my god. I haven't done it to that much, but I definitely haven't, like, I've turned my, or like I've gotten the skin like raw a bit just from like wiping my nose. I never like ripped it though. Gee, that's a great emote. Amount of eigenvalues isn't guaranteed for R 2x2. Right. That's why that's why I was trying to explain it simply, but I kept getting caught up in like the technical stuff. Most, like, I've heard it said that you can prove that like the measure or whatever of the number of matrices without a complete set of eigenvalues is like 0, and the measure of matrices with complete eigenvalues is 1. Something like that, as a way of saying that like not having 2 eigenvalues is rare. If you take the determinant isn't that the scale, which is being multiplied by, so what does determinant being 0 even mean? It does have something to do with scaling, but the determinant is not that helpful for interpreting the effect on an actual vector like this. It's the scale. It's not quite the scaling of just a single vector, unfortunately. Yeah, Leo, sorry, that's what I meant with like repeated versus distinct. Oh, nice. Suck now. I'll open that up in the background. I won't like watch it now, but just bring up a tab with that. So if the determinant is 0, there might be a different case where this happens too. Or there might be like something that I'm leaving out here, but the determinant is 0. I think of it as like a projection where you're kind of losing a dimension of your vectors, where if you have a determinant 0 vector, and you apply it to like this vector, it might get mapped onto just the x-axis now, or something, and like you don't necessarily zero out a component, but you're in a way you're losing a dimension. You should have infinite measure with complex eigenvalues too. Yeah, and so there's like a thing with like the Jacobian that like we could talk about determinants, but I think that's getting a little in the weeds. No worries, Thunder, that's fair. Yeah, Leo, I guess I hadn't thought about it that far, so I was worried that like there could be another thing that it's doing besides that, but I think we can always say that. Okay. I need to make a decision about what to do. I think we're just gonna choose PDEs. Rip that vector, he was so cool. That vector will be missed. All right, let's read this question. So working on a subset of Rn, Dirichlet boundaries, homogeneous Dirichlet even. We set the solution to go to 0. The question is how quickly we can compute this, the change in time. One equation is following. If there's a constant lambda of omega greater than 0, such as for all smooth functions. I really hate that. I know why they're calling it a constant, but I hate that this is a function that they're calling a constant. I know why, but it's just, it's got to be a better way. There's a constant. I gotta figure out what this sentence means here. Might be a stupid question. What does a matrix tell us? I get that it's just an array of numbers. What information does it give? 2 by 1 represents vectors. What about 2 by 2 or 4 by 3? Yeah, I think Leo is kind of giving a better perspective than I was about to give here. Linear algebra is a very general field. Anything that's linear, which you can tell by the name, can be expressed as a linear algebra problem. So the way that students are pretty much always introduced to linear algebra is pretty much what I just said, where you think of it as vectors are just like these arrows in the xy plane or xyz or whatever. And you think of matrices as just like modifying these vectors in some way. That's always true, but it's kind of limited. Or it's like there's a bigger picture that you miss out by only thinking about it in this way. About to finish linear algebra 3. Can't wait to be done with this. I mean, linear algebra is awesome and it's helpful. So, before walking into the building. So, like, especially if you do something like machine learning or something, like you use linear algebra a lot for that, but you think about it in a very different way. I'm trying to think of a good way to express this. I don't know. I'm kind of I'm trying to think of a good example that doesn't get too deep. Wish you could do human learning. Okay, so this is maybe just a little bit too much, but like this actually is not machine learning what I'm about to describe. I'm mixing my terminology because I learned about it. The class also talked about machine learning. This was before we talked about machine learning, though. Something that I did is we had a 2 by 2 matrix that represented a video. Basically, I might get this backwards, but the columns were each frame of the video, and the rows were all of the pixels just like stacked up into one vector. And linear algebra lets you do all sorts of cool things with a matrix like this. Like there's something called principal component analysis that you can use to kind of to mathematically figure out what is the most common thing across each of these frames. And if you want to like subtract out the background of a video because that stays the same and will show up, you can kind of subtract out just that part that stays the same. And I'm struggling to have a simple explanation for like that. I think that's still a little bit like non-specific and not easy to understand what I'm actually saying. But like, it's kind of hard to describe. It's like linear algebra. It's just kind of everywhere, and it's hard to choose like just one thing. Linear algebra is the science of lasers. I mean, they're in there too with like how the light can bounce and stuff. Linear logger. That sounds nice. Linear algebra is useful in material science too. Oh, I bet. Obtuse baboon. Babu. That's a fun name. Yeah, exactly. It's simultaneous equations too. Oh, right, Thunder. I'll look at that in a second. Linear algebra is that all finite dimensional, probably most infinite linear mappings can be expressed as a matrix multiplication. Yes. Exactly. And so like there's like dynamical systems where you have like basically multivariable differential equations. and linear algebra is really helpful for analyzing these. So I don't know. Let me catch up with Chad, and then we'll look at what Thunder sent. Self-setting, they say just a bunch of numbers combined so nothing pops up in my head. Same vector space, I could at least imagine it. Yeah, no worries, Anti-King. Hope that was just a little something, but it's yeah, it's hard to express just how useful linear algebra is, because you tend to be working on something else, and then linear algebra suddenly like pops up at you. Hi, Aditya. Hope you're doing well. Linear algebra done right. That is a good book from what I've heard. I'm doing good. How about you? Most metric things for going to uni. Oh, if you're doing this before uni, you're setting yourself up really well. Random matrix theory, a lot of that is motivated by number theory problems. You model a lot of groups. Ooh, I've heard of random matrix theory, and I've done like a tiny bit with it. I don't know you can use it for number theory though. It's also interesting because you just write the input in some basis and apply linearity, and the matrix basically falls out. Noise. So it's general to the Minkowski metric and Schwarzschild metric. Are you sure those aren't tensors? Maybe for like Minkowski is nice enough that it could be a matrix. Oh, I understand what you're asking about now, Thunder. So this is what Thunder sent in connection to the question from before about eigenvalues and eigenvectors being kind of like invariant lines, and what the determinant being equal to 0 actually means. Okay, yeah, that makes sense, Leo. That's why the matrix divided two equations, dt parts gets canceled. I've never heard of doing that, Aditya. Well, maybe I sort of have. The way I'm used to solving a system like that is to use eigenvalues and eigenvectors. But I think that actually probably works too. Okay, so the reason we want the determinant of this to be equal to 0 is just in so this is a system of equations, and we're trying to figure it out for a particular vector xy. The determinant 0 thing just kind of falls out here. Like I don't know if there's much to interpret here. Maybe I'll read what syntax is saying in a second, because that might be an interpretation for it. But really, all we're doing is we're trying to solve for a lambda x and y, and the best way to do that is to subtract this vector to the other side. Lambda is the eigenvalue. It's just we're interested in vectors that, so like the x and y here matching means that the direction is staying the same after this linear transformation, but there might be some scaling, and that's what the lambda represents. We don't really care what the scaling is, but we do want to find it. As long as it's not like 0, we don't get any, well, it could be repeated too. So like we sometimes get care about the scale. We just want to make sure it's not a bad situation. I wouldn't say just parallel, but I would say exactly like in line. Because in linear algebra, you never, or at least I don't think we don't really ever have vectors that are just like that. I would say it's more like they're on top of each other and pointing the same way. So it's still like parallel. I just think like parallel is a little bit like general, I guess. So, sorry, I may be like misinterpreting your words. Parallel is just like, I don't want it to be misinterpreted because it is a little more like general. But if you just mean like pointing the same way, then yes. Studied Calc 1 to 3, linear algebra 1 up until Eigen's first order ODEs. What do you guys think I should study next to help with college math? Gonna go to major math in CS. You want to go to grad school for math. You want to research about applied math. Okay, so if you're doing applied math, I would definitely recommend real analysis as like the next good thing to learn. You're in really good shape already though. Like, I think multivariable calculus, real analysis, and linear algebra are like the most important things for applied math. And you already have 2 of those. Linear algebra cross into real analysis? Maybe. I'm not sure, to be honest. Same unit vector. Yeah, same unit vector. I just want to make sure like we weren't, because like parallel lines, like you're allowed to like translate them up and down, and you never really do that in linear algebra because that's not linear. If a matrix determinant wasn't 0, it would be invertible. Then that's null space, which we're considering is just the 0 vector. Complex analysis is great too. It's something also helpful. It's better to I didn't see real analysis in Anti-King's list, and I think that's like probably better to learn before complex analysis. Yeah, honestly, I'm trying to figure out what syntax is like. I know it's right, but I'm trying to figure out why what syntax is saying is important. If it wasn't 0, it would be invertible. That's this null space is just the 0 vector. If the null space was the 0 vector, I guess we wouldn't get anything interesting. Oh, yeah, PhD, that's a good question. Let me just talk about this linear algebra thing for another like minute or two, and then I can talk about that, and then potentially come back to linear algebra. So Thunder, I think what Tedex is saying, or it's right, but it's maybe, to be honest, like it's maybe like a little bit like, but confusing. I'm still trying to figure out for myself. I really just think of the reason we require this to be 0. It's really just a problem. Like, we got this equation naturally just by trying to solve, first by solving for lambda. So we subtract this vector over to the other side, and we just happen to have a 0 here. All we're doing from this point is taking the determinant of each side, and the determinant of 0 is 0. So I think of there's a reason why it does have to be true, but I just kind of think of it as a coincidence. To be honest, it's not a coincidence from the sound of it, but I personally haven't read too much into it. Um, yeah, it is sketchy to say determinant of each side when the xy is there. Actually, yeah, you're right, Leo. There's a problem that the 0 is a vector. Math is hard. Okay. Line isn't perfect if you're talking about material sciences. If you'll find slight deviations, you'll look straight at the human eye. It's actually cockeyed. Oh, okay, interesting sock now. Insertia, determinant equals 0, not full rank. XY is a non-zero vector in the null space. Welcome in. Yeah, I think that's true. So, hmm. Yeah, ax equals 0, or sorry, ax equals lambda x. Let me just a minus lambda I times x equals 0. There we go. Okay, this is more like what I was trying to figure out. So you don't think it's the English word for it? I feel like I've heard people say primitive matrices and I figured out what it means. I don't remember now though. Aditya. Yeah, I know like how to solve for the characteristic equation. It's just that's not the thing I'm trying to do right now. Okay, so Thunder, let's talk about the null space first. So if you just have some matrix A, the null space is the collection of vectors x that solve this equation. And it's basically like how, so like x equals 0 always works, but for certain, if the determinant of a matrix is 0, then there's also going to be other vectors also. And so we kind of call the vector of 0 like trivial. And so what we have with the eigenvalue stuff is just we're trying to find the null space of a slightly different matrix now. Vectors are the chillest and have the biggest arrows. I'm bummed by how late eigenstuff was in my book. Yeah, it's kind of interesting to do eigenstuff as early as Thunder seems to be doing it. I don't want to keep Peach waiting for much longer, so let me kind of quickly talk about Kronecker delta and Dirac delta. So I know of a lot of applications for Dirac delta. Kronecker delta, I usually think that's more of a convenience than something that you use all that frequently. But a great use of Dirac delta is Dirac delta functions have this neat property that if you integrate, let's just say over R, let's not deal with multivariable stuff for now. F of, oh, I think I'm writing this slightly wrong. I'm getting this wrong. I should just look at the Wikipedia page. Why? Where's the property? Here we go. Okay, so if your Dirac delta function is centered at 0, x minus y is okay. Okay, I was just like worried that wasn't quite right. Mazza55, thank you for the follow. So this property of the Dirac delta function is really useful. This is like I think it's why you posted this in Zach's chat too, and you mentioned like wondering about like the filtering properties that those functions have. And I say this is like how a Dirac delta function can filter a function, where you can integrate a function over its entire domain, but if you multiply it with the Dirac delta, you just get 1 point of the function out. And so what this means is this is like a helpful thing in it's something I don't fully understand for myself, so I'm showing for the words to say it. But you can think of any function as a combination of a bunch of these integrals, and this is a form of superposition, and that's kind of what leads into Green's functions. No way the algorithm's recommending you a math stream. Oh, nice, Mazza. Welcome in. I do also play games on stream, so sometimes people get recommended a math stream when they're like when they haven't watched a math stream before. Welcome in, though. I appreciate you being here. Trying to find it. This is more general than just PDEs, I think. Wait, is this? Oh, I guess it's in Laplace's equation. Where the hell? Okay, finally. Here it's the part that I'm thinking of. If so, like, it's not even important. This is particular to Laplace's equation. This applies to ordinary differential equations also. If you can solve a differential equation that has a delta function for the inhomogeneous part, you can think of any other inhomogeneous differential equation as just like the inhomogeneous part is just a combination of delta functions. And so you can kind of build up a solution of a differential equation using a bunch of delta functions as one use for them. So Green's functions are basically how you do that. There's a lot of lectures on YouTube. This is like a new chill type of stream. Oh, awesome. Mazza. Yeah, so I'm not the only one on Twitch who does this. Whenever I see a new face, I do like to let them know that this niche exists here on Twitch. It's not just me. I'm not saying follow every last person on that list, but hey Vossen, homogenized D's. Some point you don't see a number bigger than 2. I mean, sort of, yeah, anti-king. You usually just use letters. So yeah, this niche exists on Twitch. I think it's really cool. There's a bunch of different styles for these math streams. I'm a grad student, so I've been doing a lot of like homework on stream recently, but yeah, welcome in. Okay, and so that's one use of delta functions. Another use is I know in physics, like if you suddenly like push something, you could represent that push might be your initial condition, and you would represent that as a Dirac delta function because it's just like so like sudden, and then it stops again. And there's a different thing with random walks that I know of too with the heat equation. So rather than if you set the normal homogeneous heat equation, and this is completely different from Green's functions. And let's say you have an initial condition of the Dirac delta function. Yeah, that's a really cool connection that the heat equation has with random walks. It has to be assigned. You've dug a massive hole for yourself. You need to lock in ASAP or you're cooked. Oh, are you taking a class? And I'll catch up with what you're saying, Thunder, in a minute. So as it turns out, if you were to solve the heat equation with this initial condition, I think your domain would be the entire real line. The initial condition represents where your random walk starts at the origin. And the solution you get from the heat equation is your expected location as the random walk progresses over time. So for early time, it'll be something close to the center and spiky, because you're expected to not stray too far early on a random walk. And then as time goes on, it'll kind of flatten out, because you could be anywhere the longer the time goes on. And so yeah, the delta function is nice for starting at a single point. In that case. So yeah, I think that's what I can think of with the delta or the Dirac delta function. For Kronecker delta, I think that is just a notational convenience, but maybe there's something that I'm missing. Like, it's just easier to do a Kronecker delta than a bunch of piecewise functions. I forget where I was using these. Last quarter, maybe it was for my machine learning class. Ooh, this looks a little familiar. Oh, whoa, this has the same property? That's kind of sick. You know what? Let me bring out my notebook. So I do think it was for my machine learning class we're using Kronecker delta. I'm just going to skim through it quickly and see if I can find it. I think it was early on in the class. Not seeing it yet. Why am I scrolling? I don't know why that scrolled. Oh, I think I was hitting the spacebar. If I can't find it quickly, I'm gonna give up. But let me just see if I can if I can do this. Not seeing any deltas. Oh, here's a delta. Now what? Oh, okay, yeah. It was a convenient way to express orthogonality. So we were saying so we were talking about Fourier series and how and really important property of Fourier series is how sine and cosine, or even sine and sine, are orthogonal. So if you have the integral of 0 to 2 pi sine of kx times sine of lx dx, it's equal to pi times Kronecker delta of k comma l. So this is an example of why it's just like a convenience, I think. It's just easier than writing it's either 0 or 1 if k and l match. So that's my only experience with the Kronecker delta that I can think of. Okay, let me scroll up in chat and see what I missed. So we can come back to the linear algebra stuff. Consistency is inconsistent equations, consistent inconsistent systems. Every system of equations to get sheaf prisms and stuff. Maybe, I don't know what a sheaf actually is. Preparing for your uni entrance exam, the competition in your country is crazy. Ooh, that's interesting. Mess. I've heard of some crazy like India has a pretty crazy entrance exam. Good luck with yours. Or at least the advanced one is crazy. The non-advanced one is more reasonable, but still hard. Um, just seeing if there's anything to respond to in chat. You tell me to learn from my exam. They have really bad notes. Oh no. Some other university books are always great. Haunted Mouse. I think linear algebra becomes easier once you start doing something more applied. Physics or ML. Yeah. Okay. So yeah, thank you for the question, Peach Tea. Here's some more direct proof. If T has a non-zero eigenvector, T minus limit has a null space of at least dimension 1. Sure, by rank nullity it means T has rank at most n minus 1. If you are reduced to triangular, you necessarily have at least 1, 0 in the diagonal. Really? Oh, for T minus lambda. Or wait. No, I don't know. Yeah, links are turned on, Mazza. You can post it if you want. Current something you hated in the beginning, absolutely love right now. Ooh, what do you use them for, Lothreek? Oh, a Google Drive? I don't know if I want to click on a Google Drive link. I'm sorry. I thought it was going to be like a... If you want to tell me something to Google, I'll do that, but Google Drive's a little... Google Drive can be a little... It can be anything. Chieffication mentioned? I don't know anything about chieffication. Thunder mentioned sheaves, but now she does feel a lot more intuitive once you start messing with vectors while programming. Oh yeah, that too. Oh, okay, so you're also working on JE. I'm just gonna click on the first one, I guess. Oh, okay, it's just a benchmark. In quantum mechanics? Oh, fair enough. Okay. Quantum mechanics would be cool to learn one day. His dad died by opening a Google Drive link dangerous stuff. If it was just like a public website, I mind it less, but like I don't know. I feel a bit more sketched out by Google Drive. Thunder, I am too. It's okay. Yeah, insertion. I really do not like JE questions. I usually don't work on them if someone asks me to. I don't know which one you would want me to look at, or if there's a different thing. I'm too Don to understand this. You should never be too Don. It's a dangerous thing. Um, but yeah, I have looked at JE questions before, and they're kind of crazy. Like the mains is better, but it's still like a lot. Um, but yeah, and so sure, I appreciate you like saying that proof. I'm sort of following it. I'm just like trying to like go quick, and it's hard for me to figure things out quickly. Oh yeah, like at least American high school students that definitely would not do well on a JE test. I wouldn't do well on JE test even with my current knowledge. IAT, good, not just tricky for. Oh, okay. I don't know what CMI is. Kartikeya. Okay, the spoon story again? Are you talking about when I was when I figured out that your reflection's upside down in a spoon? Is that a story? Uh oh, okay. Kartikeya. I don't think I can. Your current understanding of why you say determinant is zero for the equation is simply just to get an answer for lambda. That's pretty much my understanding too, and that hasn't steered me wrong yet. Like, zero comes up because of this manipulation that we do here. Like, we're subtracting off the right side, so we have a zero. So yeah, I don't think it's wrong. Maybe there's something deeper you could say too. But yeah. We'll read a question or two. We said to look at part B specifically. I think I maybe you're saying that in a different context, but when I said determinant of zero is zero, I was kind of wrong because that was the vector of zeros and not a matrix of zeros. But maybe you're talking about it properly. Suppose 5 complex numbers. Vertice regular pentagon. Circle of radius 2. Let me zoom in case it's hard to read on stream. Well, this is just annoying. No, I am absolutely not doing this question. Oh my god. This is a university entrance exam. Oh, and Mazza, I guess I'm a postgrad. I'm studying for a master's in applied math. Hey, Aeneas. Let R alpha be counterclockwise rotation by angle alpha. Wait, is this not R2 to R2? Oh wait, okay, yeah, okay, never mind. I don't know why they're defining what R2 is. Hey, Ayush. It's alpha reflection in the line that makes counterclockwise. Oh my god. This is probably a linear algebra question. Fixed integration seem easy. Contest math tricks seems like it. .1% even less students take the CMI Masu JE. Yeah, fair enough, Mazza. Lothric. Well, so maybe you're talking about something else. Like, you could have a matrix of zeros, but when you're doing this eigenvalue thing, this is a vector, so it's not quite right to say the determinant of each side. This is like a null space problem though, and you can say the determinant of this matrix must be zero. But like I guess you might be saying this correctly, but I said a similar thing before, and I was wrong. It's not, you're not taking the determinant of each side of this equation. You're taking the determinant of this and setting it equal to 0. Yeah, it's just like a subtle difference in the phrasing, but it's like this is the left side is a vector and the right side is a vector. But yeah, let's determine equal to 0 because we're looking for the null space of this matrix. B2 seems easy. Oh, is that the one with the oh no, never mind. Maybe I didn't read it fully. Max. Okay, so this is something called the kernel, also Thunder. But just forget about eigenvalues for now. If you remove the equal sign in the middle, left and right side, yes. So the null space, it's related, but it's a completely like we don't need anything about eigenvalues for this thing that I'm about to explain. The null space of a matrix A is the set of vectors X that get mapped to the 0 vector. Yeah, sure, Ayush. And so you can show that if the determinant of the matrix is not 0, the only vector in the null space is this trivial 0 vector. If the determinant of the matrix is 0, then there's going to be the 0 vector, but also some other vectors mixed in. So an example of like the null space, if I choose like this matrix, this is definitely going to have a null space. You see? Okay, good. And so you can always set up an equation like this if you want to actually figure out what the null space is. But yeah, it happens whenever you have like a row of zeros, basically. So for this one, like, this would have a null space. As long as X is 0, Y can be anything it wants. So I'll just call it A. Or you could say like, or even 0, 1 is an example. Oh yeah, yeah, that's a good point, Insertia. Oh yeah, so Mazza, for biology, I can there is science streams. Oh shoot, is there an S on the end or not? Okay, I got it right. That's the biology streamer that comes to mind. Chemistry, I don't know of a chemistry streamer specifically. He was in the list I posted earlier, but Actual Education does know some chemistry and can help with like questions. He doesn't necessarily focus on chemistry though. But yeah, there's a general kind of education niche on Twitch. It's not very big. Yeah, like search education in the search bar or look in the science and technology category on Twitch, and you'll find a lot of different. There's like a lot of like space streams too, if that's something that interests you. As for Jade, if you know a lot of facts and practice everything, eventually becomes easy. That makes sense in Sersha. It's just a lot of like memorization, which is why I don't really like working on those questions. So yeah, and that's why I'm saying this is a null space problem, because like we have a different matrix than just A, but we're still trying to find the null space of this A minus lambda I matrix. Can you think of A minus lambda I V kind of like a quadratic equation? For a 2x2 matrix, you do get a quadratic equation. So if you want to talk about the determinant of A minus lambda I, Let me use the matrix I was using before as an example. So 3, 2, 1, 0. Oops, with the lambdas. When you take this determinant, AD minus BC, equal to 0, this is a quadratic equation. And you just solve that for lambda. Now, if you have a 3x3 matrix, though, you get a cubic, and 4x4 is a quartic, and so on. But for 2x2s, it basically is a quadratic equation. If you made an entrance exam, bottom level 99% of people will get zeros. Yeah, fair. That's why you just give up on JE and engineering, try out academia. Yeah, I understand why it's so brutal, but it's like, and I don't have a better solution, but it really sucks that like it's just arbitrarily freaking impossible. You want to practice for Putnam? Ooh, cool. So I mean, oh wait, how is I don't know how they're graded. Like, how good is a 10 or scoring? Oh, is 10 the maximum? Oh, 10 is the maximum on one question. Okay. Which is still almost impossible to get. We're like a minus lambda I and the vector multiplied together. Uh, One question got full score. Okay. Social inexplicable hatred for high T bros. 10 is one problem out of 12. Okay. Yeah, I would be happy if I got a 1 on a Putnam question. Right, Lothric. So mm, so Thunder, there's two different ways that I'm interpreting you. So are like when you solve a quadratic equation, you sometimes have like x minus 1 times x plus 2 equals 0, and you split it off into two separate equations. Are you talking about that? Or do you mean this is literally a quadratic equation like as it is now? Oh, okay, no, you do mean this. Okay. Um I would say that's wrong. Well, yeah. It'll get you the right result. It's I'm struggling because I think that there's something to be said that you sort of are doing this. Um, there's something about this that just it can't be technically correct. Um, I'm having a hard time saying why. But like this sort of thing, it would get you the right answer. You would need to know, like, so this is a matrix, and this needs to be a matrix of zeros. Which actually, okay. Yeah, it maybe the issue is that if A minus lambda I is some 2 by 2 matrix, it means you have a 2 by 2 matrix literally equal to all zeros, which is different from the determinant being 0. I think maybe that's the issue. Yeah, law 3, we're not taking the determinant of the 0 vector. It's just like the phrasing. It's a little bit tricky. Um, it has to be singular because that's how we like. That's the equation that we happen to get. We want it to be equal to 0. Being equal to 0 means that it's singular. Hey Slim, the idea is that linear transformation A minus lambda I needs to have a non-trivial null space. Yeah, Slim. That's what we've been kind of saying, but it's like it's kind of hard to like break this down, I guess. Fizzbuzz! Hope you're doing well. It's always good to hear from you. Uh, oh, is this thinking of it directly as a quadratic? Huh. You multiply each side? Well, that's kind of crazy. You must be secretly taking the determinant here, right? X y equals 0. Oh yeah, I mean that's not a big constraint. Okay, so um it is a lovely polynomial. So what Insertia did is basically give a way that you could kind of justify thinking about this like a quadratic. I mean, it's not exactly what Thunder was asking about, though. Okay, so I think the reason that I think this is technically wrong is that A minus lambda I is not going to be the matrix of zeros, usually. We need to make it clear that it's the determinant that's equal to just the scalar 0. That's what I don't like about this, but yeah, I honestly would try not to think about this like this. Like I think it's better as you progress through linear algebra to think of A minus lambda I as a matrix, and we're trying to find its null space. And I know you haven't learned about that yet, but you almost certainly will, or at least you hopefully will, because that's a really important thing in linear algebra. You handcuffs lightning, put thunder in jail. Minus lambda is invertible. X is the null matrix. You meant invertible. You guys recommended me a book for real analysis. You search bit. Hugh's book looks good. The standard one for real analysis would be like its nickname is Baby Rudin. Rudin is the author, and he has 2 real analysis books. One of them is like a massive one that's super in depth. The other one is a baby one that's shorter and a lot easier to digest. I think it has a blue cover. That's like the standard kind of recommendation. I don't know much about real analysis textbooks for myself. I want there to be a non-zero vector x such that ax equals lambda x. H scales x by lambda, equivalent to a minus lambda I x equals 0. And if the linear transformation a minus lambda I is not injective, a minus lambda I is not injective, a minus lambda I not bijective, not invertible. Oh, is it red? Maybe I'm getting it mixed up. Understanding analysis? Okay. I never took a real analysis class. Like I've just taken Zach's like unofficial one. The hardcover is blue. Oh, okay. This is it actually has a Wikipedia page. That's interesting. But yeah, a classmate of mine was actually like just to tell me how useful this book was for the PDEs class that we're in. Like a lot of proofs in this book could be directly applied to like the PD problems that we've been working on here. It is the classic. Understand understanding analysis book. Abbott, okay. So this one is also being thrown around. You found it so boring it made you cry? Really? I mean, I haven't read it for myself. Knowledge obsessed me. Pick a color. Two textbooks to study with. Second book is Stephen Arley. Okay. I can figure out what injective means in this context, Thunder. It's going to be something about the matrix not being full rank, I think. This is taking forever to load, and it's not that important. Intro real analysis bored you to tears. You're still crying. Haven't stopped. I would probably be bored in most intro real analysis. I think I would still be bored in most real analysis classes, even if it wasn't intro. But Zach eats a 2i pie makes it a lot cooler. Johnson bot and Pfaffenberger or Pfaffenberger. I don't know. Finish mathematical analysis. The metric space stuff is a little extra for a beginner. Oh wow. Yeah, metric space. Beginning with that is kind of crazy. Okay. I think 2i pi is easier to read in the username, Leo. We don't usually write it like 2i pi though, that's true. And earlier analysis finding like division theorems all working together like pipes and stuff. Yeah, it does like it is really neat how everything slots together to give you the fundamental theorem of calculus. Like I was surprised by how short the proof for the fundamental theorem of calculus is if you like just take the mean value theorem for integrals for granted. There's a whole bunch of machinery that you have to learn before that, but the actual proof itself is like surprisingly short. So yeah, Thunder, I'm happy to keep on talking about linear algebra. I don't know if you feel like you've been grilled enough for one day though, so let me know. Otherwise, I'm just gonna pick out a PD's problem. You give up? Okay, that's the spirit. No, I mean, I almost never understand things on the first try, Thunder. I need to like learn it once, and then I realize I don't understand it, and I come back to it the next day and the next day, and eventually it sinks in. Understanding compactness, open, close, and its use in proofs. True, yeah. Should do a numerical example. I still want to like overwhelm Thunder. We've talked about a lot of like kind of deep stuff. So it might be better to take a break at this point. Never understand F equals MABS from before. I You were asking a good question there. Yeah, yeah, Leo, it is deeper than it looks. Like it's not like we take it for granted that those two things are equal, but it's actually not as obvious as you would think. Or it's not as simple as it might look. Okay, I'm reading problem 1 on this right now. So domain is bounded and there's constant temperature 0 at the boundary. Does the bounded domain really affect anything? The question is how quickly we can compute this, which I did do this in the midterm. Implication is the following: if there's a constant lambda of omega greater than 0. Right, I was struggling with this sentence here. For all smooth functions f map omega to r that vanish on the boundary. Wait, should this be Rn? I assume it's Rn. Maybe not. I don't know. Sounds good. Mazza, enjoy. That vanish on the boundary. Gradient, the magnitude of the gradient squared is greater than... Oh, what the hell is this even saying? We can bound the rate of ascent, the square of it, or like the total of all these rates, by some constant that depends only on the geometry, times the square of the volume underneath F. Ugh. Oh my god. Let me get up with chat. I'll help me slay the Spire too. It'll inspire you to beat it. I don't know. Are we Dirac? Hey, underscore. We might. It might be in the background. We haven't talked about energy methods for the heat equation yet. We've done the Dirichlet energy for the Laplace's equation though. I don't know how it works for the heat equation. F is d dl dv dt. Ma is dl d. Oh, with Lagrangians. Oh, true. Fizzbuzz. Has to be R. You're integrating the value of F. I don't know. It's a real output, but a vector input function? Okay. Hey, Raven. Wait, do you change your color? You used to be purple. We could argue... You did. Okay. It's a nice color. It's exponential decay of the L2 norm. Uh... Okay, sure. We're bounding the change in time by above by a negative number. Why don't we already have this from above though? Okay, well, we're trying to figure out the rate. This is just that it decays. It doesn't tell you anything about the rate, I guess? Find lambda of omega. Oh yeah, okay, so this does have to be r. It's not r to the n, because f is basically the same thing as u, and u is omega to r. For each omega proper subset of Rn to be the largest constant c greater than 0. What the hell? Prove lambda of r to the n is 0? Well, I feel like this is already, like, omega's a proper subset of Rn, and we're plugging in Rn, but okay. The largest constant c greater than or equal to 0, such that diamond is satisfied for all smooth functions that vanish on the boundary. Prove that lambda of r to the n is 0. Suppose lambda r to the n is greater than 0. Find a counterexample. It's just quietly wistful. Okay, so can we find a function that's integrated over all of Rn, the magnitude of the gradient squared that comes out to be 0? Well, just the 0 function. Is that cheating? Oh wait, no. I think we're trying to find. Well, dude, I don't know. Yeah, because both sides are 0. A linear function? Uh, I'm trying to think of a function that would collapse to 0 on this side and be non-zero on this side. But I think a linear function would do the opposite. Oh, nice. Thanks for explaining that, Max. What does vanish from the boundary of omega equals Rn? Yeah, omega is some proper subset of Rn, so it's compactly supported, and it goes to 0 on the boundary of omega. Yeah, it's because my professor isn't that careful with his wording. We're supposed to pretend that lambda of Rn is allowed for the purposes of this part of the question, I assume. It does literally go against how he defined omega, but that's just how he rolls. He doesn't care about the technicalities. Um, I'm not sure it should be 0. Hmm. Yeah, like we're saying that like omega is specifically a proper subset of Rn though. That that's why this there's definitely an error in this question, and my professor refuses to fix typos. He says to figure it out. I mean, if there's a serious one, he'll tell you like what he meant, but like for the most part, his response is to figure it out for yourself. So that's our job. Let me get a screenshot of this and bring it into the journal. Yeah, he has very strong feelings about how to teach a class properly, and I disagree with almost all of them. I'm not a fan of how he runs his classes. Um, so like, what types of functions have 0 gradient? No, Zach, he is almost the opposite of you in every way. Actually, okay, so like he talks about his teaching philosophy a lot because maybe he's like nervous that we don't like him because of it. But his big thing is that you have to learn or you have to struggle in order to learn, and I agree with that. But he interprets that as meaning he should help you as little as possible. Um, and so he just puts up the proof on the board as he thinks it should be presented, and it's your problem if you don't get it, basically. Yeah. And I've gone to his office hours and asked him for help on the homework, and he literally just told me to look over my notes and ask me what could be helpful. And it's like, dude, I spent hours trying to do that. If I'm asking you, it's because I'm stuck on the problem. uh, limit n lambda omega n goes to 0. Well, I think we need to define a lot more stuff before this makes sense. Insertia. What is the sequence of omegas? Surely he can make the L2 norm of a gradient arbitrarily small for a bump function. Ooh. Started finding the number 0. I mean, insertia, I guess, sure, but if, like, don't we need this to show this? So I'm not sure how this is helpful. Or wait, maybe I'm misinterpreting you. Never mind. Maybe I don't know. So he said it was probably bad. I mean, that's fair. I appreciate you even trying. A bump function is interesting to think about. So, sounds good, Thunder. Thanks for the question. Sleep well. And the sub? Thank you so much, Thunder. I appreciate that. Easy. How would we... I mean, the issue is that with a bump function, don't we need to flatten out the maximum at the same time as we flatten out the gradient, though? Yeah, I just used a bump function in my last homework, too. To do something different. Yeah, because like we don't want a bump function that gets narrow like that, because that has a really big gradient. But if we flatten it like vertically instead, we're reducing our maximum at the same time, so we might get a 0 equals 0 situation. Non-zero, we just want a function non-zero maximum, 0 gradient, which I think the mean value theorem would beg to differ with that. Lambda v unbounded is equal to the supremum of omega bounded in v. What? Is v the entire thing of Rn? Driveling liar? Hey. I mean, you're welcome to feel that way. What's happening on the screen is something that's crazy and complicated, but part of my goal. And Shane, thank you so much for the raid, Shane. Welcome in, people. This is actually good timing. So Shane, I hope your stream was good. I saw that you were playing with plastic. I hope that was fun. I'm excited for next week. I was just telling Driveling Liar, who was new here in chat, that part of my goal for the stream is to make math kind of more accessible and more interesting to people who don't like math. What's happening on the screen right now is definitely not accomplishing that because for people who are new here from Shane's stream, I'm a master's student studying applied math. And the way that I can make streaming work in my life right now is to kind of do homework on stream. And this is how my homework looks. So yeah, those are integrals. Like these things here, but these are like a more complicated integral. And so yeah, people on my end, please check out Shane. I really enjoy his stream. History, sociology, all those good things. And from Thursday of next week through Sunday, I believe, there will be a big extravaganza. I forget what he's been calling it, but basically there's going to be a whole bunch of guests on his stream, including me, who will be kind of talking about what they all do. And so I'll be giving a little talk. I have my talk like half figured out, I just need to kind of, I have all the math and coding that I want done. I just need to kind of organize it better and figure out what I want to say. It goes by many names. Epic crossover stream event. There we go. Yep. So I'll be on Saturday, and once like I see Shane post his announcement in his Discord, I'll post an announcement in mine. Shane Posium, Shane Extravaganza. I love it. Okay, let me catch up with chat now. Too easy to think. Going by instinct, you would start with the last equation for omega 2. Check if I can use inequalities to change omega 2 to omega 1. Oh, yeah, maybe Slim. You can tell I love mathematics because I'm a dribbling liar. Oh, I get it now, dribbling liar. I didn't even connect that. That's fair. Signs seem to help get the inequalities that you need, like the negative sign on the right-hand side. Okay. Proving the second part is trivial. Maybe the second part is meant as a hint. Maybe. I don't know. The F stand for summations? That's true, yeah. Dribbling liar says, call the sine function rotated pi over 4 radians counterclockwise about the origin of f of x. Pi over 4. Strictly bring your own food. Shanapalooza. I love it, Silver. Hope you're doing well. Free pens? I mean, you can ask for a free pen. I don't know. I'm not giving out pens. So wait, let me see what... I do know some complex analysis. Shame branded conference style bags. That'd be fun. Just make it like a con where everyone brings their own like branded stuff. Sine function. Oh wait. I was thinking of a phase shift, dribbling liar. Are you thinking of literally taking a sine wave and doing this with it? I don't think this is a function anymore. Really? Huh. Asymptotic equivalent to f of x. Oh, that's... Yeah. I guess it should be. So... I'm planning to talk about how we model the spread of disease, and I'm hoping to do that in a way that only uses high school math. I think it's still going to be a little bit complicated, but I'm doing my best to figure out a way to make it simple. Yeah, at SAR models. Sine prime 0 is 1. Oh, okay, fair enough, Max. I remember we talked about a question like that a few weeks ago, I think. How do we... No worries, Shane. Thank you so much for the raid. Enjoy your food. Much love. Man, I've been craving funnel cake. I haven't eaten a funnel cake since I was a kid at the boardwalk. And I've been seeing at Trader Joe's, they have frozen funnel cake, and I've been tempted to buy it, but I feel like it's not going to be as good as if you get it from an actual like carnival or boardwalk or something. Parametrics. How do we use parametrics? Do we multiply this by a rotation matrix? What's the rotation matrix? Is it cosine? I need to Google it every time. I can never remember. It's like cosine, cosine, or something. Maybe like there's only one minus sign. Rotation matrix. Multiply the input? Really? Oh wait, why am I doing it on that side? Cosine pi over 4 is root 2 over 2. For proving lambda Rn equals 0, if S is a Gaussian of width S, L2 norm 1, integral of grad squared Rn is 1 over 2S squared. Wait. Is it Gaussian? We need 1 over 2S squared greater than or equal to lambda Rn. Oh, you're saying we can make the left side arbitrarily small. Like if we have a very large S, fizzbuzz? I'm writing out lambda instead of just drawing the symbol? Huh. I mean, Gaussians are great. They kind of have a way of showing up everywhere. Yeah, I can never remember the normalization. Four S squared. I didn't realize it was a 4 too. Oh, maybe I'm used to having the 2 inside the parentheses for the squared. 2 pi S squared. First extra factor of 1/2 because we square root's an extra factor of a half. We square it to get 1. Oh, okay, yeah, because there's a squared built into the definition. Okay. That is funny. Hey, Anshu. Okay, that's an interesting argument, Fizzbuzz. Thank you. Okay, have a bunch of math you could explain to a basic level. I think, as far as I know, only me and Zach will be the math streamers who are doing it. There's gonna be a lot of like philosophy streamers, at least one art streamer. I don't know everyone who's gonna be doing it though. Shane's announced some people in his Discord, but he's still waiting for confirmation from others before fully announcing it. What Raven? Sorry, I don't know what you're saying. What about philosophy? Oh yeah, if you're interested in philosophy streams, dribbling liar, there are many people who I could shout out. Oh, oh, you'll be doing it, Silver. That's awesome. Hopefully, I can catch it. You just arrived? Oh, okay, Raven. We're talking about both about this PD's homework problem, and then also this question that dribbling liar posted here. Is this doing what I want it to do? I don't know how to test this. Like, would Desmos graph this? If we actually do this multiplication, I think Desmos would graph this. Make it into a vector. Yeah. I think I know how to do this. Let's find out. Desmos, the interface is almost too clean, where it can be... I always forget what the syntax is. Because it doesn't... Oh my god, what am I doing? Square root 2 over 2 t minus sine t. Square root 2 over 2 t plus sine t. 0 t 100? Ooh! Look at that baby! That's fun. Okay, so we've expressed this parametrically. Now we just need to remember how integrals and derivatives work for parametric functions. Paul? Someone give me Paul. Will this be Calc 2? I guess tangents? Okay, so maybe... Can we just figure out what this formula should be? We're starting with 0 to pi over 2 root df dx dx. So if we chain rule pi over root 2, oh, thank you. We're gonna have df dt dt dx. And then dx dt is equal to root 2 over 2 1 minus cosine t. So okay. Well, I'm just gonna say, I guess times dx dt dt. Do the bounds of integration need to change when we do this though? I think they do. If x is like, I think this step already isn't necessarily valid. If x equals 0, hey chaotic diamond, how's it going? I guess t equals 0 here. Are we gonna get an equation that's very hard to solve over here though? I assume you, maybe not. This might be a special case where it's easy to solve. This is just pi, isn't it? Oh, nice. So t equals pi gives... Nice. Okay. 0 to pi. SQL calculus low-key super chill with an application of derivatives? Oh, hell yeah. So you're doing like related rates? Because usually that's not chill in my experience. If you're finding it chill, that's great though. Oh god, I'm out of room. Okay, let's plug things in. Wait, what the hell is FT? DFDT. Oh, it's dy. You're right. I should maybe convert that f into a y, because that's easier for me to think about. Dy dt is wait. Dy. It's just dy dt divided by dx dt. Ugh, okay. I'm making that y. Okay. So dy dt is root 2 over 2, 1 plus cosine t divided by dx dt, which is root 2 over 2, 1 minus cosine t, all square rooted, times dx dt, root 2 over 2, 1 minus cosine t dt. Okay, this is our problem. Jeez. I think, no, I don't know. Let's cancel out some constants at least. We could write it 1 minus cosine t, 1 plus cosine t, dt. Is this a good thing or a bad thing? This feels like there's a clever u sub here. Able to ace my log higher derivatives test, which is supposed to be the hardest test. Ooh. Because very slow pace. Also this case. Oh, true, Zach. Yeah. Calculus only covers for 75%. Oh, okay. Fair enough. Well, that's good. Calculus is not easy to learn, so the gentler it can be, the better. Sine t dt, one of the trickiest integrals because it's minus cosine, right? It's really easy to forget that minus. From 0 to pi. Root 2 over 2, positive 1, minus... Why am I blanking? Wait. Cosine of pi is negative 1, so we get positive 1. Then we minus... But we're minusing a minus, so isn't it 1 plus 1? So it's root 2. Okay, good. I was about to get 0 and I was getting confused. So this is just root 2. Nice. This is a good review for me. Did the music stop, by the way? It did. Get me my robot music then. We'll play it with... We'll use the song. Wait. Oh, I did the wrong thing. Go to song radio. Okay. Hey, collar cone. By the way, I have something to give you. I don't know if it'll show up on your screen immediately, or maybe you need to refresh. But you have a fancy new diamond. Yeah, thank you for the question, Shriveling Liar. If you're interested in math in general, I don't know if I already did this. I'm sorry if I did. There's a math streamer niche on Twitch. It's not just me. So I just like to shout out whenever I see a new face that this niche exists here on Twitch. No worries, color cone. I feel like you're just always so like enthusiastic to talk about math, and I really love it. So it's always good to have you around. Oh, is Order One bot broken? I didn't even think about how I haven't seen you use it in a minute. Did Twitch update their API or something? Oh, you just need a new opt token. Hopefully that's not too hard. I guess they didn't like change up their endpoints. Oh, do you have to like apply for it? I've only done that. I've only done that for real once to get my background lights to work, and it was pretty painless for them. You'll be a center of a special group's attention. That's right, Clonk. You're gonna get attention. You're gonna be a massive streamer. You have an active mind and a keen imagination. Oh, that's nice. Um. Okay, so prove if omega 1 is a subset of omega 2, then wait, why is the constant greater? I would have thought the opposite. Oh, does that have a name? Poincare inequality. Famished, why did that get auto-modded? How dare you say how many viewers I have, apparently. um, I don't know. But it's because I got a raid first from Zach, and then I got a raid from Shane also. So that's why it's not a like all natural. It didn't automod you. But funny enough, I do have one math stream where I got over 100 viewers, but again because of raids. But that's because of a DayZ streamer that I'm friends with rated me, not realizing that I was doing math at the time. So they were really confused. This does look like Poincare's identity inequality. And to be the next Kai CNAT? Oh my god. I don't know about that. I'd love to be able to have a big enough stream to make a living, but I don't even like watching streams that are too big. Like once they start getting like 200 viewers, things get kind of crazy. And I appreciate you for being here, Clonk. For P equals 2. Oh yeah, by the way, famous Zach is a Zach, like Z-A-C-H. I keep seeing you say Z-A-C-C-K. Um, is there anything we can get from this Wikipedia page that'll be helpful? Maybe I shouldn't look at the Wikipedia page. Maybe I should. Actually, okay. Let's see if they do the subset thing. Oh yeah, I doubt he cares, but I guess I care though. Hmm. What does Wolfram have to say about this? Not much. Wait, it's the constant on the other side. The L2 norm of f is less than. Okay, yeah, the constant is on the other side. Oh, I wonder if there's a simpler proof. So, wait. Uh, no, it has to be smooth. No, a proof of the first part, I mean. Okay, no, oh shoot, in Dribbling Liar, you put another question in chat that my eyes skipped over and I just remembered now. I was thinking of a non-smooth function that might be a good thing to use here, but we do need it smooth. Dribbling Liar earlier said this. A guy with no life. Welcome in. Do I use AI? For the longest time, I specifically did not use AI. But honestly, I am AI. A particular class that I've been in, for this class I was just looking at the homework for here too, I've actually broken down and I've started to use AI to help learn certain like background things. So I'd say my use is limited, but I've kind of feel like I have to use it now. The AI, yeah, it's true. Zach is the original, is the original AI. And limit as r goes to infinity, the contour integral along a circle of radius r of the gamma function. Well, that's kind of tricky to not consider integer, like negative integer values. Because I feel like this is that even proper to do? So this is the complex plane. Like there's poles all along the negative real axis. I feel like it's kind of cheating to just say ignore those poles and take them as r goes to infinity. Like that's going to change the residue. Is that the point, I guess? Like somehow figuring out the limit of these residues? Here in GPT 5.5 has been solving novel problems in combinatorics. Oh, maybe. To be honest, just out of curiosity, I've given Chat GPT some of my homework problems, and it actually does kind of well. Like it would probably get like a B. Could also just ask for the limit of the Cauchy principal value. Would principal value rescue that? Like I think if you're being super rigorous, maybe that's not your point. I assume you would need a contour. It'll be like a weird keyhole contour. The answer is 1 over E? Interesting. Papadoria slash Piggy Master? Sure. I want to think about this problem for a bit more first, but... yeah, let me see. So... I mean, this would be 0, though. This is analytic, right? Or no, never mind. The polls will contribute something. Thanks, thanks, Koshi. Let me bring up my complex analysis textbook. I'm a little rusty. Another tuna sandwich. You're gonna be half to tuna pretty soon, famished. Sounds good, Papadoria. Okay, so it's 2 pi I times the sum of the residues. Insertion, you're probably right, because we do need to be probably need to be enclosing them. I'm rusty on exactly how contour integration works, but I assume the question is just asking us to like do what you're saying and just kind of take like some of these residues out to infinity. Oh wait, that's what the principal value thing would save. I see what you mean now, dribbling liar. Like if you did do it at an integer, you just say the principal value. Wait, what is that for? Color cone? Is that for this gamma function question? How do you find residues again? I know it's the coefficient of the 1 over z term, but it's kind of a pain to find often, isn't it? Like gamma, is that? Ugh. Let's just look at the Wikipedia page. Right, it's that limit formula. If they are simple. I hope they're simple. It'd be annoying if they're not. How do we figure out if they are simple for the gamma function? We need its Laurent series, I guess. I don't want to calculate this. I'm not going to calculate this all this by hand. Just throwing you my dirty computation. Da 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 da. Listening is just 2 pi over e. If we do get the series for e out of this, that'd be kind of fun. Or e to the minus 1, as you're saying. What am I trying to find? I guess I'm looking for just the Laurent series. Wait, oh wait, is it even analytic though? It's faster than exponential. I don't know. Maybe I'm looking for the wrong thing. I don't know how do you find the degree of a pole for a non-analytic function? I don't know if what I'm saying is even making sense. Wait, so okay, fair, yeah. So I do remember that formula with the limits. I'm just curious, like, how do we show that they're simple poles? I'm okay with, I guess, not doing that too. Uh, do we want to look at the integral definition here? I guess n is a negative integer here. Let me bring up the integral formula. 0 to infinity t to the z minus 1 e to the minus t dt. Oh, really? I guess you need to include 0 also, because 0 is also a pole. Yeah, I might settle for just looking at a proof, because I don't know if I can do this. Yeah, thank you for linking that. Yeah, and I'd rather not spend an hour just calculating this. By poles of gamma function. I kind of want to see what this is about too, but we'll look through this first. Oh, using... Oh, wait, what? Oh, this is just a... Okay, so that... Oh, what the hell? Okay, so, like, they're using this top, the numerator, times gamma, and a property of gamma that is basically a factorial to combine it into one. Oh! And that gives you a cancellation with that and that. Um... Okay, and then this is kind of using, again, a factorial type of property. Yeah, that's what I was getting confused on too. Like, I don't know how you if gamma blows up faster than exponential at its poles, I don't know how you are supposed to find the residue at that pole. Like, it seems like something gets broken there. Like, how's residue even defined? Because my thought is that it probably doesn't have a convergent Laurent series, but maybe I'm wrong. Should I always find the order of the pole using the zeta function functional equation? Okay. But okay, so you cleverly factor out a -1 to the n to flip all these signs? Huh. Oh, okay, yeah, I see where that comes from. And that's just n factorial. So this is e to the -1. So yeah, in Sersha, you were right. 2 pi I divided by e. I wonder if there's a reason for that. That's kind of cool. The Weier's transform of the gamma function. Is that an Euler macaroni gamma in there? Might be too small to see on stream. Yeah, clearly do not tend to 0. I look at this and I know exactly what's happening here. Macaroni makes another appearance. Gamma of 0 is equal to gamma 1 over 0, which make it a simple pull. Well, that seems a little sketchy to me. Gamma of 0 isn't defined, though. I don't know if I don't think I understand that tripling wire. No, because like not all zeros are the same though. That's what I don't like about it. So the factors of the continued product clearly do not tend to 0. Okay, yeah, neither of these things will. Well, what do they mean by tend? Like, what values of z are they talking about? Because this could be 0 if z equals -n. Well, that's the point. Okay. And this automatically gives you that it's a simple pole? Because this is 1 over gamma? Oh, as n goes to infinity, that... Okay, we're not changing z, we're changing n. That's what you're saying. Maybe. Okay, I think I understand it. So I had no clue this form existed, but that does make it really easy to figure out that the poles are simple. Or at least, well really easy is an exaggeration, but a lot easier. The gamma difference equation proves that gamma is analytic on C without the poles. Gamma is analytic for the real part greater than 0. Really? That's surprising. Or is this just analytic as in, well, I don't know. It's so easy if a 5-year-old can figure it out, probably. Is this a different definition of analytic? Is it just the derivative is well defined? No. The gamma function is faster than exponential. Shouldn't it not have a convergent Laurent series? I thought that was like the condition to be analytic. Like the gamma function I thought is too fast. Suppressed singularity infinity is inessential. I think, yeah, Fizzbuzz, I guess that's what I'm thinking of. For finite Z, I guess it could be. I don't know. How do they figure out the residue? Oh, they don't do the residue on this. Do they do the residue but before? Oh, yeah, da da da. Okay. Whew. So the most useful products of math have always have something sketchy about them. Okay, maybe we'll take a look at Papadoria's problems now. I don't know. Yeah, this is neat. What I'm trying to I'm trying to apply things that I learned from like my asymptotic analysis class to the gamma function, but I only learned about it in terms of complex numbers, and I think everything is the same. Or sorry, in terms of real numbers, and I think everything is the same when it comes to complex numbers. But I think there's some weirdness that I'm not thinking about correctly. Um. Okay. Let me find Papadoria. Three, 5, 6, 9, 10, and 12 are best. They're not meant to be hard, just stupid. Okay. The integral of square root x. I can't do a Russian accent. You see the same problem. You can't talk about the pole of e to the 1 over z at z equals 0. Same with gamma. Okay. Yeah, I think that I that must be my issue, Fizzbuzz. You're right. Because yeah, Taylor series for E are fine, just not at infinity. Um, at FNHC, yeah, I can certainly talk about that. Have you done complex analysis before, or like any sort of complex analysis? If no, that's okay. That just like changes how I'm gonna explain things. Gamma-like functions that uniformly converge to gamma. I assume those gamma-like functions need to be polynomials. Isn't it because I care about gamma? If gamma wasn't analytic, I wouldn't care about it. Which ones did Papadoria say? 3, 5. Okay, so let's start with 3. And FNHD, once I hear back from you, I'm happy to talk about poles. Sigmox and numbers. Okay. So yeah, before we get into this problem, let me talk about poles to FNHG. So a pole, I guess for now we just talk about real numbers. The same thing is true for complex numbers though. A pole is just a place where a function blows up to infinity. So like the function 1 over x has a pole at 0 because it looks like this. And so it's one is blowing up to positive infinity, the other is blowing up to negative infinity, but that's fine. It's still a pole. Like we can't define it at 0. And not all poles are the same though. So there's a difference between the pole that 1 over x has at 0 and a pole that 1 over x squared has at 0. And I don't mean the sign. It's actually like maybe even so even ignoring the part where like 1 is negative and 1 is positive, there's still a big difference outside of that, which is the rate that they go to infinity is actually kind of important. 1 over x squared goes to infinity a lot faster than 1 over x. And we can say the same thing, like 1 over x cubed goes even faster. And so I think if you're only talking about real numbers, I don't know if there's that much more to say about poles. But the reason that they're so interesting and good to know is when you start talking about complex numbers. So for a complex number, they're kind of harder to draw because you kind of need 2 numbers for the input and you get 2 numbers out for the output. But if I set up my real and imaginary axes for like the inputs, let's talk about the function f of z equals 1 over z. So kind of like the same thing here, just we're allowing different types of, we're just allowing like complex numbers for inputs. We can plug in any complex number we want except for z equals 0. And so, yeah, and so we can use colors to kind of like express inputs versus outputs, but I don't want to care too much about that right now. And so often in complex analysis, we're doing what are called contour integrals, and depending how deep you went in physics, you might have seen these before. So in physics, like you might have like a point charge at the origin if you're doing like E and M, and then you want to figure out the work done along a path like that's like that, I guess. And so that's an example of a contour integral just with real numbers. We can do the exact same thing with complex numbers, a contour in the complex plane. And as it turns out, if you integrate along a contour away from this pole, like, and it's a closed contour, your contour integral is always 0. And so we would say that it's like, you might have seen this symbol before, like an integral with a circle in it. F of z dz, and the c means closed contour, meaning it like starts where it ends. An open contour would be like it starts here and ends somewhere else. I don't know if you call it open, but it's not closed at least. So it equals 0 if f of z has no poles. Or if c does not enclose poles of f of z. The contour integral, yeah, as Dribbling Liar says, we kind of are evaluating the function at each point on this contour and adding everything up. So like we evaluate here, add it to evaluated here. And we often contour integrals show up a lot because it for real integrals. So like if you have a real integral from negative infinity to infinity of just some real function like x squared, why not? You can think of that as like a contour in the complex plane. Except it just goes along the real axis, starting at negative real infinity and going to positive real infinity. X squared is simple enough that we don't need to worry about complex numbers, but there are different types of integrals that are a lot more difficult. And you actually do a trick where you take this real problem and you make it complex by, say, adding like a circular arc here. And understanding poles and what is about to get to, which is called a residue, actually makes a real integral much easier to solve via complex numbers, and you still get a real answer back out. I did not mean 1 over x squared. I was just trying to name any random function that doesn't have a pole at 0. I didn't. Well, yeah. I wanted to avoid there being a pole at 0 because a pole being on the contour is a little bit weirder. So yeah, for a nice function like x squared, this entire contour is closed and there's no poles anywhere. So the entire contour integral will just be 0, and we don't get too much, like, this is kind of a stupid integral. It's going to blow up to infinity, so there's not much to say about this one. Oh yeah, but traveling wire does give a better example of an integral that does converge to an actual number. And you don't need complex numbers for this, but you could use them if you wanted to make your life harder. So this is just arctangent. If you integrate it, you might end up getting 0 actually, because arctan is odd. No, no, you don't. You get a positive number. And that makes sense. Where am I going with this? So if you did, like, if you really want to shoehorn in complex numbers where you don't need them, just like as a demonstration. So whenever x squared plus 1, there is no real number that breaks this function. You can plug in any real number you want. You never get a denominator of 0. If you allow complex numbers, though, plus and minus I would break it. So we have poles at positive I and negative I. And so suddenly this contour is enclosing one pole. This pole down here doesn't affect anything. It's outside of our contour. We don't care about it. This pole in here changes everything, though. This thing here no longer applies because we do enclose a pole now. And so there's this miraculous formula called the residue theorem that tells you what the answer is in this situation. I guess yeah. So the integral of a function that encloses a pole is 2 pi I times the sum of the residues that are enclosed. So let's say there's n residues. In this case, we only have one. And I'm just going to name them A sub I. And residue is it's something you can calculate from a function. How do I say it? There's like a lot of machinery that I'm trying to like quickly introduce you to, but this is already a lot, and I need to introduce you to another thing before you can understand what a residue is, unfortunately. The first thing you need to go from, if you know what a Taylor series is, you need to learn about a more general version of Taylor series, which is called a Laurent series. So a Taylor series is a polynomial like c sub n times x to the n, sum everything up. This c sub n depends on the derivatives of the function. And insertia is right. A Laurent series, it says, hey, this is a nice looking thing. What if I just take this 0 and make it negative infinity instead? So we go from like a good old polynomial to something a little bit weirder. We on the right side we still have a polynomial, but on the left we get all these kind of like 1 over polynomials basically. And the residue, there's a way that you can show this, but I'll just tell you. The residue is exactly this c-1 coefficient. The coefficient of 1 over x is special because it is this residue here. And the reason for that is basically the integral of 1 over x is log of x. Whereas the integral of like 1 over x squared, for example, is just another thing involving x. Like it's that. And so this like kind of weird asymmetry with 1 over x becoming a log is what makes this term special. Yeah, there's a lot of things that I'm skipping over here, and this is normally something you would learn over the course of like an entire semester of complex analysis. But I hope you at least picked up some things from this. If you have a question, let me know. Oh, that's a really good question too. And Papador, I'm sorry that I meant to get to your question, but I really shouldn't be explaining this. So for a Laplace transform, I'm gonna need my textbook for this. Okay, good. Okay, so this is the definition of the Laplace transform here. This is the inverse Laplace transform up here. S is a complex number. And so the forward Laplace transform is relatively simple. You don't need any complex analysis for it, honestly. It's commonly taught in like differential equations classes. What the differential equation class normally skip over is the much more complicated inverse transform formula, because this is a contour integral, and usually that's not a requirement for differential equations classes. So the thing that makes it, or it's like, you could think of these both as contour integrals, but like this one is a much more complicated contour. You have a constant real part, and then you're going off to infinity in the imaginary directions. Let me just draw what this means, because that probably makes no sense when I say it in words. Okay, so S is the variable that we're concerned about here. So this axis is the real part of S. This axis is the imaginary part of S. And the thing we're integrating is the Laplace transform of F times e to the sx. So e to the sx has no poles on its own. That's fine. But f hat might have poles. And so let's say f hat has poles here, and we inherit those poles in this like definition. So we have to worry about those poles. So let's say we have a pole there, and a pole there. What we do is we choose C, that C there, so that the real part is to the right of all of these poles. And kind of the trivial part, and so we want to evaluate the integral along this blue line here. That's complicated to do on its own, and so we're going to do the same type of trick that I showed earlier with adding a circular arc. There's an immediate question of like, we could close to the left, but why not also close to the right? There's nothing inherently wrong with this. And you actually do both. It turns out like enclosing to the right is kind of trivial, but you kind of are supposed to do it. You should always just get 0, because it does not enclose any poles by the way that you've constructed it. And that corresponds, that has a physical meaning, I think. I think the fact that you get 0 just means something. I can't remember now. I'm sorry. It's been a minute since I've done this. It's kind of bothering me. I probably written down in my notebooks somewhere, but it basically it corresponds to the real part of S being more than C. The more interesting / complicated part is this integral here. Because now we are enclosing all the poles. And so for this, you would just kind of do the summation thing that we talked about of all the residues, and that would give you, they'll be in terms of x. Yeah, I don't think that's correct, Insertia. You should not get 0 for enclosing on the left. And so you'll get just like some sum of residues, that's going to be your original function back out. So the poles are telling you that like the poles are what make this work. If there were no poles anywhere, we would just always get 0 when we do this procedure. So the poles are what really actually define the original function that you had back out. Because you can find the Laurent series of f hat e to the sx and just read off this coefficient for like all 3 of these points in this case. They don't have to be 3. and you add them all up, there's an x there, so they'll be in terms of x, and so that'll happen to match your exact function. So the poles are what make your original function. Like, if the poles were somewhere else, or if there's a different number of poles, you would get a different function back out. Okay, and this is what I was struggling to remember. So closing to the right with no poles, it does give you 0, and I think that corresponds, if x is time, that corresponds to nothing happening before time 0. I'm still a little bit weirded out by that, though. So yeah, I hope that helps. Let me know if you have anything else you want to ask about here. Maybe I should give a special shout out to Zach, because he's been writing a book on differential equations, and he's been emphasizing the Laplace transform a lot. So if you have if you want to really like dig into the Laplace transform, he's been thinking about that a lot. And the functions don't have poles. Oh, so that's what, like, yeah. So what dribbling wire meant by that is a function is analytic. It's kind of tricky to say what analytic means, because it actually turns out to be a lot of different things that all mean analytic, or that are like all equivalent. For the purposes of like complex analysis, you usually just say that an analytic function is differentiable, or like, okay, let me, a function f of z, you could say the same thing for real functions though, is analytic at a point z naught, let's say, if f is differentiable in a neighborhood of z naught. So what this means is the derivative has to exist. Not just at that one point. So let's say we're interested in whether f is analytic at this point right here. We need to be able to say what the derivative is exactly at that point, but also in some circle around that point. It might be very small, but there does need to be a circle where it also exists. And the only time that's not true is when this point right here is a pole. So if we came back up to our example here with 1 over x squared plus 1, if we chose exactly positive I, the 1 over x squared plus 1 is not analytic there, because it's not differentiable exactly at I. And so if you wanted to stick with real numbers, like 1 over x is not analytic at x equals 0. And so for this, like, I think there's some subtleties where other things could also make it not analytic, but like for the purpose of like complex analysis, usually the most you need to know is that if you're dividing by 0, you're not analytic there. There could be other causes of not being analytic too, potentially. But the simple thing is just say, don't divide by 0 and you're fine. And so what Dribbling Liar said is it's maybe like a little bit confusing, because You're supposed to talk about analyticity at a point, but usually functions are analytic pretty much everywhere, if not everywhere. If a function is analytic for the entire complex plane, you would say it's entire. If it's what we were talking about a function called the gamma function earlier that has poles at 0 and at negative integers. And so we were getting kind of confused on the, like, or at least I was confusing myself on the phrasing of analytic, because gamma is analytic everywhere in the plane except at these green dots. So anywhere else you can be analytic, just not at those dots. You can be analytic even in between these dots, just not at them. And so it's kind of a confusing thing where, like, if you restrict yourself only to like the right side here, gamma is just straight up analytic. Nothing else needs to be said. If you want to think about the entire plane, though, gamma is not analytic on the entire plane because of these poles, like, mess it up. So that's why, like, the phrasing of analytic is kind of tricky because you have to always talk about it at a location. But often when we're talking about math, we're not specific about what the location is. So that leads to confusion sometimes. Oh, really? Was it originally defined just as, like, for positive numbers? Or are you just talking about, like, factorials, though? Yeah, like, I've heard it called an interpolation for the factorial function. That's a nice way of talking about it. Oh, yeah, if you mean, like, integrating along, like, the negative real line, then yeah, you'd run into, like, you probably could do some principal value thing, but it'd be really weird. Okay. So yeah, you're asking great questions at FNHC. There's anything I can think of to say right now, but if you prompt me again, I have to keep on talking about this. Otherwise, I'm gonna take a stab at Papadori's question and probably wrap up the stream soon here. I don't know why I said prompt, like I'm an AI, but that's the word that came to mind, I guess. So without using the power rule explicitly, well, can I just do this geometrically? Just derive, I mean, true. It's just a trapezoid. Um, what's the area of a trapezoid? Isn't it the average of, like, that, or isn't it average times height? Is it pi minus e over 2, or wait. Pi plus e over 2. times pi minus e. Subtract the triangle. Don't think. Oh. You know what? I'd rather just be told a formula so I can regurgitate it. Area of trapezoid. It is the average times height. Okay, nice. This actually has a cool form, doesn't it? It's pi squared minus e squared. Oh, nice. Dribbling wire. I like that. Okay, that was a quick one, so let's pull another one. 5 is another one popular said is good. With Riemann sums. Well, it's a constant function, so we don't need to be very... We don't need a very small width. Trapezoid, like turning trapezoid into a square? Yeah, that makes sense. Oh, I hate Riemann sums. So there's 70? Well, wait, let's just do 0 to 69. I'm going to choose delta x equals 1. And the height is just 1. So isn't it just 70? Or is it 69? It's 69 or 70. It should just be 69. I think I messed something up. If I do the integral not using Riemann sums, I get 69. So it must be like this, reverse engineering it. Iron Chad, the way I'm winning these Spire runs. Antiderivatives. I've always been taught it with Riemann sum as the definition. I think it's kind of cool that you can connect Riemann sums to all those, like the antiderivative definition. Or like property, I guess, if you don't define it that way. Let me pull in another. While singing a Christmas song? Oh my god. 2 for 2? Oh, 10 or 12? Okay, okay, okay. Oh my god. No, I'm not gonna do all of these, so if there's ones that you think are cooler. The macaroni and the suck function. I think it's the successor. So like the successor of 69 is 70? I assume that's what it is. We're integrating in terms of plus. That's great. 420. I hope there's a 6, 7 in one of these also. I'm gonna be sad if not. Plus the power of 70. 1 minus macaroni to the plus to the 69. D plus. Yeah, this feels like that one meme programming language. It's literally called like brainfuck, I think. It's just all like symbols. I'm looking for a U sub here. What does this buy us? Right, yeah. Whoever's the derivative An exponent is not basey. Is it times ln of the base or divided by ln of the base? That's what I never remember. Is the minus... That's true, Raven. Derivative of exponent. Exponential function. Oh, wait, what am I doing? Differentiating gives something kind of ugly. Yeah, I was hoping it would give a plus to the 70. Yeah. Just odd? Oh, is it odd? No, it's not odd. That would have been nice. Um, Wait, okay, I need to... What is a derivative of 2 to the x cubed? I need to do a simpler version of this problem. Okay, it is times ln. So it's 2 to the x cubed times ln2 chain rule times derivative of x cubed. I hope this is right. I think it's right. Okay, so this is... This is not what I want. I don't think this is the U sub. Do we integrate by parts? I don't want to integrate this by parts. This looks terrible to integrate by parts. FNHC, yeah, this might be the most important problem known to mankind. I think of nothing more important than this integral. It's not even either, I don't think, though, in Sersha. Wait, is this actually an open problem? Without the weird symbols? Could you contour this? Maybe. I'd really rather not use contour integrals, though. Okay, you know, I need to see it with normal numbers. I don't know if that'll actually help or not, but... Yeah, it's... Finite bounds are really annoying. It's possible. You just get... They just take frickin' forever. You can do, like... I think there's like a... You might need poles at either end or something. But like, like my professor was calling like a dog bone or a dumbbell contour. Maybe there's a branch cut. Like, oh yeah, we were doing with like where there's like a branch cut between these two poles. That's right. I don't know if they have to be there, but that's when we were using them. Down with analysis. I don't know what to do with this. Hmm. L subject. Can't rename it. It's okay, it didn't even help me anyway. Oh my god. Which one looks more fun? Okay, let's look at 12. E to the negative if and only if. Yeah, I was trying to figure out what this means. Like, what is this? From 3 to 3 of 3D3. I don't know what restriction is telling me, Papadori. I assume, am I not allowed to just do a U sub? Is that what this is telling me? Like, I'm not allowed to just do this directly? Yeah. Oh my god, Zach. It kind of does. Okay, yeah, I think the restriction is telling me I can't do this. Okay. Integral sign as a variable and as an operator. Okay. So, I know the answer is 1. How do we do that without that? Taylor series? Wait, Raven, did you get unfollowed? Either way, thank you. If and only if to the power of n over n factorial d if and only if. Yeah, that's what I was confused. That like the integrals in dx. You thought you get 300 coffee beans again? Oh, that's smart. I wish that worked. Unlimited coffee beans. Yeah. Dribbling. You should be writing the questions. Just make everything as cooked as possible. This isn't cooked enough. From 0 to infinity. And then, am I cheating if I go back to the... I don't think this is... I don't know if this is how you intended to do it, but... I don't know how else to do it besides Taylor series. See if and only if it's something you're gonna write on paper one day. Love to see how that gets through peer review. Okay, I don't know if you had something else in mind for this question, Papadoria, but if not, I might call it here for the day. One time, one of my friends typed a paper in LaTeX, essentially did what number 9 was doing. Had both D's in different fonts? Oh no. Actually, in general relativity, when I was studying that, there was a fair amount of like an infinitesimal amount of distance, and so they did just unironically write DD like that. Oh yeah, we're definitely gonna raid Raven. Oh, okay, okay. What is that a left? Is that just Omega with a hat? Oh, this is a really good. I guess it's like a DI table. I don't know. It's Omega hat. Okay, I can't remember what a left looks like. It's not like a normal hat though. Like the normal hat is like pointy with a corner. That's more like a like a the hat like a French painter wears. You know, it's like flat and it droops off a little bit. Getting beans is my only purpose. Okay. Um. Oh, we are this number 8. We are integrated with respect to a number. French omega. The Greeks would be sad. Using your left hand. That's funny. Bit of a complex number to note. Maybe I don't. It has like a little droopy bit that weirds me out, like right there. Anyway, sleeping mask, yeah. Oh yeah, yeah. It does look like that. If tau and omega, yeah, true. Okay, YouTube peeps, I'm gonna use stream off here. Thanks for being here on YouTube. On Twitch, we'll look for a raid.